for the invitation. Thank you for the introduction, the nice introduction and the invitation. Today I'm going to talk about dark matter schemes during warm inflation. This is based on a paper that I finished recently with Katie Fries and her PhD student at UTRC, Gabrielle Lemotte. And I just added this nice picture of your pendulum this morning. I'm a big fan of it, so that's very interesting. Okay, so this is the outline of my talk. I'm going to talk about dark matter briefly. Then I'm going to talk about producing dark matter from a thermal bath. I'm going to focus on two main directions that you can follow when you want to produce dark matter from a thermal bath, namely freeze out and freeze in. I'm going to talk about the sensitivity of dark matter abundance to the initial condition of the thermal bath. And then I'm going to talk about the possibility of having a thermal bath during inflation, which is not trivial. It's called warm inflation. And then I'm going to use that thermal bath to produce dark matter. And please stop me if you have any questions. So I think I don't have to convince the audience that dark matter exists. We have overwhelming evidence coming from different scales pointing towards the existence of dark matter. Evidence such as rotation curves of galaxies, structure formation, gravitational lensing, cosmic microwave background, and everything that we know about dark matter is based on its gravitational interaction. What's the nature of dark matter? Unfortunately, we don't know. We don't have enough knowledge. If you just think about the mass of the dark matter as one single parameter, we have 90 orders of magnitude to play with. Dark matter could be as light as 10 to the minus 22 electron volt fuzzy dark matter, or it could be very heavy as primordial black holes. And we can basically kind of partially constrain these models and these candidates. It's really hard to exclude any of these models totally. This is kind of obvious, but it's kind of, I think, important to remind ourselves that the nature of dark matter is the prospects for its detection is closely related to the production mechanism of dark matter. Well, there is an intriguing mechanism to produce dark matter, which is out of a thermal bath. In other words, I have a dominant component of the energy of the universe, which is a bath of radiation. It's in thermal equilibrium. In other words, I can describe the whole system with one single parameter, which is the temperature. And then you can imagine there are some non-gravitational interactions between this bath and dark matter. Well, then basically you have two kind of ways to produce dark matter from this thermal bath. People call them freeze out and freezing. So I'm going to just go through these mechanisms and the different features of these mechanisms, their differences, their similarities. So freeze out. So I'm going to, first of all, I'm going to fix my cosmology. I'm saying standard cosmology. By that, I mean I have a radiation-dominated universe. In other words, the thermal bath is the dominant component of the energy. And the other assumption that I'm going to make is that the initial temperature of the bath is above the mass of the dark matter. Then I'm going to turn on some non-gravitational interactions between dark matter and bath. What's going to happen is that I'm going to assume the interaction is strong enough to bring the dark matter in thermal equilibrium with the bath at early times. In other words, if you go back in time, there was a moment that actually dark matter is a part of the thermal bath. It's like radiation. And it reaches chemical equilibrium with the bath. In other words, the rate of the production of dark matter from the bath becomes equal to the rate of the annihilation of the dark matter back into radiation. And this is nice, but we know that this cannot last forever. The universe is expanding, the temperature of the bath is dropping. At some point, the temperature is going to drop below the mass of the dark matter, and dark matter starts departing from the chemical equilibrium, and that departure sets the final abundance of dark matter. That's what we call it freeze out. So the classic example of this is weakly interacting massive particles, or WIMPs. So you have two WIMPs talking to two particles in the bath. I use chi in my slides to represent dark matter. We can write down a very simple Boltzmann equation to track number density of the dark matter. So this term here takes care of the expansion of the universe. There is this parameter here, sigma b, which represents the strength of the interaction between the dark matter and the bath. And then I have two terms on the right side. This term has a negative sign. It represents the annihilation of dark matter into the radiation, which brings down the number density. And then I have a production term here with a positive sign, which gives me the production of dark matter from the bath. And when you solve this numerically, it's better to change the variables from the number density to something else that we usually call yield. And yield is the number density of the dark matter divided by the entropy density of the bath. And the reason that we do this is that because both of them, they dilute with the expansion in the same rate, you can kind of absorb the dilution because of the expansion in this from the yield. So what's going to happen is that initially I'm in thermal equilibrium, the yield follows this curve which comes from Boltzmann distribution, and at some point they're going to freeze out. They're going to depart from chemical equilibrium. In this language, the yield is going to plateau at some level. And that gives me the amount of dark matter that I have today. Of course, I need to include the dilution. But anyway, and as you can see, there is this parameter here, sigma b. If I do a simple calculation, I can find out that the final yield of dark matter is inversely proportional to the strength of this interaction. In other words, if I have a larger interaction, the dark matter is going to stay in equilibrium for a longer time. It's going to freeze out later, and I'm going to end up with less dark matter. If sigma b is small, it's going to freeze out earlier. I'm going to end up with more dark matter. So it makes sense. If you plug in numbers, you're going to find out for a weakest scale coupling and weakest scale mass for the dark matter, you're going to get the right amount of dark matter too. This is the Wien miracle. Probably you've heard about that. There is an advantage in this mechanism. It's a thermal process, and because of that, there is no memory to the initial condition. In other words, as long as the initial temperature of the bath is above the mass of the dark matter, that doesn't, you don't need to know that temperature. It doesn't enter here. That's an advantage, I think. Now, this was freeze out. We can talk about freeze in. In the freeze in, I'm looking at like the extreme opposite direction. Now, there are some general assumptions in freeze in. We usually assume that we start off with negligible amount of dark matter, basically nothing. There is some tiny production rate for dark matter from the bath. So gradually over the time we produce dark matter, but this rate is not very large. It's so small that dark matter is always getting produced, but they cannot find each other to annihilate each other or reach thermal equilibrium with the bath. So basically we're just producing them, and we kind of build up the abundance of the dark matter over the history of the universe. So what I need here is a small production rate. Now the question is that, how can I suppress the production rate? There is a simple way before getting into like more technical ways to reduce the production rate. I want to overemphasize this because it's so simple that people usually miss this. It's a kinematic argument. Imagine you still have the standard cosmology, radiation-dominated universe, and the initial temperature of the bath is much, much smaller than the mass of the dark matter. So because of this, if I want to produce particles out of the bath, I don't have enough energy in the bath. Basically, we have a thermal distribution for the particles in the bath. So thanks to Boltzmann distribution. And if I want to have enough energy to materialize dark matter out of this bath, I need to pick the particles of the radiation from the tail of the Boltzmann distribution. And that gives me this Boltzmann suppression factor. And just by doing this, you can actually reduce the production rate. You can get the freezing without doing anything about the coupling constants or anything else. So it's been kind of mentioned in this paper in 1998, and it kind of got rediscovered in 2023. But I'm not going to talk about this, but this is a possibility. Okay, now because I don't want to do that, I'm going to assume that the initial temperature of the bath is always above the mass of the dark matter. I'm just going to stay away from Boltzmann suppression. So one way to do this, remember we are trying to do freezing. I need to reduce the production rate. So I can imagine there are some renormalizable operators between dark matter and the thermal bath, and there are some coupling constants there. I'm showing them here with lambda. If I pick this lambda to be very, very small, unnaturally, which is not nice, but can do the work for me, I can reduce the production rate. So it's really easy to show that generally speaking, I mean, it depends on the model, but generally speaking, if this is the situation, you can estimate the final yield of dark matter, which goes like this. So it's proportional to the coupling constant, and it's inversely proportional to the temperature of the bath. And that's interesting. It tells me that if I start at really high temperatures, the production is not really important. If I let the universe expand and the temperature drops, the production actually goes up. Of course, there is a limit. If temperature goes below the mass of the dark matter, you still have that Boltzmann suppression. So there is this sweet spot when the temperature of the bath is of the order of the mass of the dark matter, you expect to produce most of the dark matter around that time. And after that, it doesn't really matter. Here I have a plot. Remember, this was freeze out, these curves. So to compare with freeze out, here you can see the freeze in. So you start at a very small amount of dark matter, you're building up dark matter, and then this parameter here is m over t. Let's go to 1, you produce most of the dark matter, and after that, it doesn't really matter. It's not plateaued to some constant. So because this process doesn't care about high energy, it cares about the lowest scale in the problem, which is the mass of the dark matter. They call it an IR-dominated process or IR freezing. So this was one way to do freezing from the thermal bath. There is a second way. I'm still assuming the initial temperature is above the mass of the dark matter. I don't want to go through the Boltzmann suppression. This time, I'm going to rely on non-renormalizable operators. In other words, dark matter talks to the thermal bath through these operators, and it means that they have some heavy scale with some powers downstairs, and you get the suppression on the rate because of this heavy scale being there. And to just imagine the source of this suppression, you can think about having a heavy mediator between the dark matter and the thermal bath, and that heavy mediator's mass needs to be even higher than the initial temperature of the bath. And then you can integrate that out, and in the language of effective field theory, you end up with these non-renormalizable operators. So here you don't need the small coupling constants, you get the suppression from this heavy scale. Again, you can do the simple calculation or estimates. Generally speaking, the final yield of dark matter this time goes like this. You have this suppression downstairs because it's dimension full. You end up with some powers of temperature up here. So it tells me that now in this scenario, the relative abundance of dark matter is very sensitive to the higher temperatures. Basically, everything that you produce is at the highest temperature. So again, let's look at the numerical solution. Remember, this was the freeze out. This was the IR freezing. Now I have the UV freezing. You can see just almost all of the dark matter is being produced sharply at the beginning when the temperature of the bath is the highest, and then it's going to just plateau. After that, I mean, if you zoom in, there are some tiny changes here, but it's not really important. Because this is, in this scenario, the yield of dark matter is very sensitive to the highest temperature. It's called the UV-dominated process or UV freezing. Any questions so far? Yes.
So you said that the coupling should be smaller and smaller, like in the previous case.
Yes.
But it can't be like just by the gravitational particle production for the dark matter.
Gravitational production?
Yeah.
No, I'm assuming here everything is there is not some non-gravitational interactions. You can do freeze in through just graviton, exchanging graviton. You can even do freeze out by exchanging graviton. The temperature has to be Planck scale, but I'm not talking about that. I'm just talking about some non-gravitational interactions. Yeah, but I think you can also use graviton to do freezing. Yes. Good. Well, so I'm going to focus on this UV freezing. So it seems that in the UV freezing of dark matter, the yield of dark matter is very sensitive to the highest temperature of the bath. it could be a bad thing. It seems that we have this dependence on the initial condition, but it also could be interesting because it means that maybe this way we can actually explore the initial stage of the formation of this path. We have something which is sensitive to that stage. So then we need to ask this question: what is the highest temperature of the path? Is it just an arbitrary number? What determines that? So to answer to this question, I'm going to define a parameter. That's how they define this parameter in the literature. It's the reheating temperature. It's been defined as the temperature at the onset of the radiation-dominated phase. In other words, you are basically the dominant component of the energy in the universe is going to be radiation. Other stuff are negligible. At that point, I'm going to read off the temperature of the universe. That's the reheating temperature. Well, there is another temperature, the highest temperature of the bath, with Tmax. The question is, what is the relationship between these two? We need to think about something which happens before radiation domination. It could be inflation. Let's say inflation ends at some point, and if I'm doing all the inflation, there is no radiation there. At the end of the inflation, just imagine instantaneously you transfer all the energy left in the inflaton particles into radiation. If I do that, I'm assuming the duration of this process is basically zero. It's very happens so fast that nothing changes. Then that tells me that the Tmax should be equal to the purity. Should be no change there. And after that, entropy is conserved, T drops like 1/8. So this is one situation. If this happens, the maximum temperature of the bath is actually the tube heating. But it's not really realistic because there should be some process happening after inflation, before radiation domination, and usually there is some duration for that. We can call it a non-standard cosmology. Could be, in other words, during this time, something other than radiation dominates the energy density of the universe. It could be some kind of matter. It could be the kinetic energy of inflaton or the kination. It could be something else, but it starts transferring energy into radiation, or we're producing entropy. So during this transition, the temperature doesn't follow like 1/A being the escape factor of the universe, because you have entropy reduction. But at some point, this is going to end. We're going to end in the radiation-dominated phase, and temperature is going to behave like 1/A. So now remember, temperature here is T reheating. But if I have radiation here and thermalization happens fast enough, I can also have temperature during this process. And because T is falling here, I need to go back in time and find the temperature at the beginning of this stage. And that's the Tmax. And that's what people did in around 2000. Holm and his colleagues, they looked into this. This is pre-freezing, so they didn't care about freezing. They were trying to do freeze out, but they were interested in cases that the mass of the dark matter was about the reheating temperature, and they didn't want to end up with Boltzmann suppression. So they came up with this idea that if you do the calculation carefully, you have the maximum temperature here, which is much larger than the reheating. Could be larger than 1000, depends on the parameter, but basically you have a higher temperature to begin with here. My focus in this slide is on freezing, but we need to note, pay attention that when we have non-standard cosmologies, that they can affect the Hubble rate. We can also change the freeze out of dark matter. I'm not going to talk about that effect here, but it has been studied in literature. One example is in this paper by Boscar, but I'm not going to talk about that.
One question. You
Sure.
don't need inflation, right? I can create that situation by some decay of.
Exactly. Yeah, it's an example. Even in inflation, you can imagine the inflaton is decaying.
Yeah.
It can be a heavy particle, of course. You need some transition.
And it can happen at any time prior to BBN.
Prior to BBN, that's true. That's true. That's a fair point. Yeah, that's just an example. It doesn't have to be exactly. Okay, so I'm going to go back to the UV freezing, and I'm going to think about UV freezing during reheating prior to radiation domination. So If you remember, I showed you that in the UV freezing, the abundance of dark matter is very sensitive to the highest temperature. Now we know that if I have something before radiation domination, the highest temperature of the bath can be actually very large, larger than what we usually expect. So people they realize this. This is now after they discovered freezing. So they started looking at UV freezing of dark matter using like different non-standard cosmologies. So in these two papers, they look at just the matter domination before radiation domination. So now you have some kind of matter dominating the energy density of the universe, decaying into radiation. At the same time, you're also producing dark matter out of this radiation. And then there were other people, they looked at like almost all other kind of different non-standard cosmologies. I borrowed this plot from this paper. You can see they look at the equation of the state of the universe, omega, and they can kind of play with this. So it can be anywhere. You can have matter, you can have kination, you can have some interesting potentials that give you large omegas. And they looked at this process of producing dark matter after doing this kind of non-standard cosmologies. And they defined a parameter. They estimated the amount of dark matter being produced from UV freezing during these non-standard cosmologies, and they compared that with the amount of dark matter that you would produce at the reheating temperature. And they found that this is actually, you get a really huge enhancement. It's proportional to the Tmax over T reheating with some powers, and this power is related to the dimension of that non-renormalizable operator. And so, in other words, you can produce more dark matter by UV freezing if you consider like what happened prior to radiation domination. Any questions so far? Okay, so one can ask a silly question that what about like everything that these people they've done is just using the heating. So they're assuming inflation ends, you have a reheating process, and then, or you have some non-standard cosmology, and then you have radiation domination. So somebody can ask this question, what about inflation itself? Can we push this even further back in time and start producing dark matter through UV freezing during inflation? So it sounds this doesn't sound like a really smart question, because our understanding of inflation tells us that during inflation, you're just exponentially expanding the universe, you don't have a thermal bath. How do you want to do that? You need to first have a thermal bath during inflation to be able to do freezing from that thermal bath. So actually this can happen. So this has been done. In other words, there are situations that you can have the inflaton doing inflation for you, meanwhile having a thermal bath coexisting with the inflationary phase. They call it warm inflation in contrast with the cold inflation. So I'm going to talk about that for a while, because I didn't know anything about warm inflation. Some people, they don't know anything about warm inflation. So I just want to talk about that in a few slides before getting into producing dark matter from that. Is there any question about this so far? No, good. Okay, let's start with the cold inflations. The idea behind inflation is that we use an early period of accelerated expansion to drive the universe towards homogeneity, isotropy, flatness. It's very nice, works very well. I mean, it has its own issues, depends. Different people have different opinions, but it's a very nice, simple formalism. The easy way to do this is by having a scalar field living on top of its flat potential for a while, and it starts slow rolling toward the minimum of the potential. While you are up here, this potential energy dominates the energy density of the universe. You get the accelerated expansion. You want to have enough number of equals of inflation, so you need to stay here for a while. And then at some point, this is going to end. The field is going to end up at the minimum of its potential. It decays into radiation and it hits the universe. I can write down an equation for the evolution of this field, scalar field. I have two terms here. One is coming from the Hubble. They call it like a friction term, which doesn't allow the field to slow roll. And then I have a dissipation term. And the reason that I have this is, remember, we want to, at the end of the inflation, when the inflaton field is sitting here, we want to reheat the universe. It tells me that there should be some coupling between the inflaton field and other particles. So there should be some dissipation here. In the cold inflation, this term is initially at the beginning of the inflation is negligible compared to the Hubble rate. So you can actually drop this in your calculation, take your inflationary phase, and when you're down here, this term becomes important, becomes dominant, and eventually decays into particles, and you heat the universe. So this is cold inflation. Now, what is warm inflation? So in 1995, Barrera wrote a paper on this. So this was his idea back then. He wanted to, this is the same equation that I showed you, the dissipation term here coming from interactions between inflaton and some other fields. So Barrera assumed that this dissipation term is not negligible. Even from the beginning of the inflation, it can be large, it can be comparable with the Hubble. So if I do that, if I put a noticeable term here, which I can neglect, it tells me that then some part of the energy of the inflaton field is getting dissipated into radiation. In other words, I can also at the same time write down an equation for the energy density of the radiation. The production term on the right side comes from this term. And the Friedman equation tells me how Hubble changes with time. So Barrera wanted to keep this term here, make it kind of sizable, comparable with the Hubble, and he wanted to get inflation at the same time. And there was one other thing that I think I forgot to mention here. In the cold inflation, one of the nice things about cold inflation is that we can explain the inhomogeneities in the universe that we observe in CMB as the quantum fluctuations of the inflaton field. So in other words, the fluctuations that we can see in the universe, their source in the inflation story, it comes from quantum fluctuations of the inflaton field. In warm inflation, they actually come from thermal fluctuations of the inflaton field. In other words, the origin of inhomogeneities in the universe, it's going to become classic, it's not quantum. This is one of the big differences between warm inflation and cold inflation. So this is like the phenomenology of the warm inflation. You still want to inflate, which means that the energy density of the inflaton should dominate over the energy density of the radiation, at least for, I don't know, 60 volts or so. You are going to produce non-Gaussianities. That's one of the predictions of generally.
Is this still allowed by
Yeah, I mean, yes, it depends, but yeah, it's one of the predictions. You get the relatively large non-Gaussianities. Yeah.
Also,
Right. Yes. 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 I mean, there are models. They are surviving, but that's a good point. Yes. You want the dissipation coefficient here, upsilon, to be. It can even get even larger than Hubble given the inflation towards the end of the inflation. Usually, this is in contrast to the cold inflation, and of course, you want to stay in the slow roll regime because you want to get enough inflation. So we demand the maximum of these two terms to be larger than the mass of the inflaton. And the last thing is very important in warm inflation. You want the temperature of the bath to be larger than Hubble, so that the thermal fluctuations, they dominate over quantum fluctuations. Okay, let's say this can happen. Let's say this is possible. What would be the consequences? So these are the consequences, some of. So remember, you have a new dissipation term here, which is sizable, it's important. Because of that, I have a new thermal friction term in my equation, which allows sub-Planckian field excursion, even for very steep potentials, which is good. And the other nice feature about warm inflation is that here I have a plot of the evolution of the energy density of the inflaton field in black, and the evolution of energy density of radiation in red. So you can see we start with energy density of the inflaton to be larger than the radiation, which makes sense. That's what we want. We want to have inflation, but you are dumping some of this energy into radiation. And at some point towards the end of the inflation, the radiation is going to start dominating the energy density of the universe. So there is this kind of smooth transition from the inflationary phase to radiation domination. In other words, I do not need necessarily a separate heating mechanism. There is this it's kind of a built-in aspect of this model, which is also good. It can also, because of this, you can have inflation, can do inflation with potentials that they don't have a minimum in principle. And there are some observational predictions for this kind of models. Basically, they give you a really suppressed tensor to scale ratio, the parameter little r, and also large non-Gaussianities. Okay, this looks good, but what's the catch, right? So if you think about this, if you want to build a model like right to Lagrangian for this is challenging because you are coupling in flaton into light degrees of freedom. So why this is problematic? The reason is that if I have some light degrees of freedom, having couplings to inflaton, because of the field excursion of the inflaton, these light degrees of freedom, they can pick up large masses just from interacting with inflaton. And remember, the rate of the interaction here is not really small because we want the dissipation to play a role. There is another problem. There would be a back reaction from the light degrees of freedom on the inflaton field. There would be quantum corrections, thermal corrections, and they can spoil the flatness of the potential. So that's bad. So this is so bad that in 1998, Andre Miguel wrote a paper with this title, "Is warm inflation possible?" Which usually when you put this in the title, the answer is usually no. And I think that one of the reasons that warm inflation is not really, maybe it's not really popular, maybe it was because of this paper. But people, they didn't stop. They tried to come up with a model, this proof of existence, that we can do this. So they did this in 1999, Brera with some other people, they came up with this model. It's called distributed mass model. So you have a potential for the inflation. And remember the tricky part was coupling inflaton to light degrees of freedom. So you can imagine I have some light fermions and some light scalars, and I'm going to couple them to inflaton. The way that they did this is through these terms. So they introduced by hand these different mass terms here. And the idea is that when the inflaton evolves, the field value at some point gets very close to these mass numbers, that the difference becomes negligible, these particles become light, then you can excite them thermally and do the dissipation. But let's try it. You have to, like, for 6 equals, you have to add so many fields to do this, and then you have so many fields, they're gonna back react with the inflaton, so they had to add supersymmetry to control the thermal corrections, but they show that it works. It's a model that you can get the warm inflation from, but it wasn't really a simple pretty model. Again, it took them several years, I guess. In 2016, they came up with a simpler model. They call it warm little inflaton. And the idea, they got some ideas from little Higgs models. What they had in mind was they had some two scalars. They talk to a U1 gauge field, you have a Higgsing mechanism happening, you break a symmetry, you end up with a pseudo Nambu-Goldstone boson. Effectively, after breaking that symmetry, you get terms like this in your Lagrangian. So now what they do, they have this inflaton field, they couple that to two fermions, and through that symmetry breaking process, you induce these terms in your Lagrangian. And you can see now the field value is inside this cosine and sine terms. So it's kind of bounded. It's not going to blow up the mass of this psi1 and psi2 fields. And they also show that if you do the calculation, the back reaction, the quantum correction on the mass of the inflaton is going to cancel out. So everything was fine. And then they use these fields, psi1 and psi2, to couple them to light degrees of freedom. They're going to decay into light particles, which is going to be radiation. So it's like you need to have two sets of fields. I think they call these fields the psi1 and psi2, like the kind of catalyst, and the radiation comes from these light fields. And this way you can avoid those problems, and it works. You can go do the calculation. It's actually in agreement with the observation. I mean, it depends on the potential that you put here, but you can get some successful inflationary scenarios. But this is 2016. There was some recent progress on warm inflation in 2019. David Kaplan and his colleagues, they came up with another model, they call it minimal warm inflation. So in this setup, inflaton is an axion-like particle. It has a potential, and it talks to some Yang-Mills gauge fields living in some arbitrary SUN. It doesn't have to be SU3, QCD, or anything else. It's just some SUN. And they realized that by having this, first of all, you have shift symmetry for this inflaton this time. That's going to protect you from thermal corrections and quantum corrections to some extent. Of course, by introducing this potential, you're going to break that symmetry to some extent, but it can be okay. And they showed that the corrections are not that bad. But the point is that then this field can dissipate into gauge fields. They showed that there are some Sphaler configurations for these gauge fields that at high temperatures, you can excite those, there are transitions between those. So you get a really nice thermal friction rate just from the Sphaler transition between different configurations of gauge fields. And the other interesting things that these people found later on is that in this type of scenarios, the warm inflation is actually inevitable. Most of the parameters of in the model, even if you start at the vacuum, you're going to excite these gauge fields, and it's like an attractor solution. Most of the times, you're going to end up with a thermal bath during the inflation. So it's not something that you want to make. It's already there most of the times. You have to include it into your calculation. Any question about these models? Oh, I do not have it. It's you need to look at the calculation. It's not really, yeah. I mean, there was this in this paper, they didn't really go into details. They made some claims, but in this paper, there's some appendix. They showed even you start at the vacuum, you're going to excite some quantum states, and then you get to a thermal state really fast. Yeah.
So V5 probably they constructed V5.
V5 is it's V5. You can put almost anything that you want as long as you're not messing around with other things. But you're going to break the nice things about the shift symmetry is going to be broken somehow. But you need to be careful about that, how much you're breaking that symmetry. Yeah. I mean, these ideas, they've been around, like doing dissipating energy from inflaton to gauge fields. But I think this was new because they looked into this Sphaler transition. So they are saying actually most of the effect comes from a topological nature. It's not really a quantum or thermal thing. It's in principle, it's because you have different vacua, and then at high temperatures you can excite them. They can give you a really high rate of dissipation. Good. So I'm going to go through this really quickly. So as I said, if you can see, there are basically 3 or maybe a few concrete models for warm inflation. So if you look at the literature, what people usually do, sometimes they pick one of these models, and then you need to, because you have a Lagrangian now, you can calculate the dissipation rate from the first principle. Then this is not easy, it's thermal QFT. And then when you have everything ready, then you need to go and confront this with observation, make sure you can get a really nice inflationary result. This is one approach. Again, as I said, there are a few models that you can do the whole thing there. There is a phenomenological approach. The people, they don't have a model, they pick a potential, they assume something for the dissipation rate. But from just looking at this model, they realize that usually this dissipation rate is a function of the inflation and temperature, and they usually pick some power law for temperature, and then they do their calculation. So this is what they do usually. Okay, now to get the feeling of warm inflation, I'm showing you this. This is what are we talking about? Like, what is the cosmology in these models? So this is the warm little inflaton model, one of the first simple models that people found. And if you, for example, have a quartic potential, you can show in this model that the inflation rate is linear in temperature. You can plug this into your equations. You can find the evolution of the temperature and the inflaton field as a function of time. So on this plot, you can see these parameters. So on the x-axis, I have the e-fold from 0 to 60 e-folds and beyond that. On the y-axis, I have dimensionless numbers. This is ratio. So the green curve here shows you the ratio of the energy density of the infrared cone divided by the energy density of the radiation. And you can see initially it's peak, towards the end of the inflation, it becomes of order of 1, and then it drops. The temperature goes like this in a typical warm inflation model. It's almost constant, but it decreases by time, and towards the radiation domination phase, it drops. And then I have also the Hubble constant. It has a behavior that you can see. It is kind of starts constant, but it changes towards the end of the inflation. Right. And here there is this point that inflation ends. There is a transition between the end of the inflation and the beginning of radiation domination. And then you have the radiation dominated phase. Basically, this point here is the repeating point for us. And to find that, we define this parameter epsilon h. And when you start radiation domination, this is basically 2. In other words, the equation of the state is 1/3. That's how we define the heating. So this is just to show you, like, to get the feeling of warm inflation cosmology. Now I'm going to use this setup, not at some point this model, but I'm going to use this setup back to my the starting point. I'm going to produce dark matter through UV freezing from this. So let's do that. So this is my contribution. So far it was just review. So this is the setup. I have an infrared field. It has some dissipation to a thermal bath. So I have a warm inflation story going on here. And the thermal bath talks to the dark matter through some non-renormalizable operators, some high-dimensional operators. And we want to study the production of dark matter through the inflation and after that and see what is happening. Can we get anything out of this or not? And so my colleagues, they came up with this thing. So warm inflation while ultra freeze in, they got it modified. Anyway, so this is the cosmology, simple equations that I showed you. On the dark matter production side, this is very simple. I have a higher dimensional operator. You can think about the process like 2 particles going to n plus 2 particles. I can write down a Boltzmann equation to trace the number density of this particle. It goes like this. Remember, it's a freeze in. So I just have a production term on the right side, which depends on some powers of the temperature and some powers of the scale here. Very simple. But remember, the problem here is that H and T, they have a non-trivial behavior with defaults. I need to go and pick a warm inflationary model, solve it, and then I have H and T as a function of time. Yes?
So like in this, the rho R equation, basically my RHS, the source is proportional to like rho phi, and that is like larger. So how do I maintain the rho R to be small?
It's not compared to rho phi. It could be
Yeah,
like
but
one.
the source is large, right? The source, the RHS term, looks like it is
It's
large.
the source is comparable with the Hubble, but you can always keep this hierarchy. You can, let's take a look at this. You can numbers here, for example. It can be, I mean, I don't know if this, yeah, you can start here. If you can still get the inflation. The point is being that you need to have enough energy to give you like a kind of a semi-de Sitter background evolution.
But you do solve like both of the like both.
Oh yeah, you need to
rho phi,
exactly. You need to solve exactly. Even this dissipation term, it depends on temperature and the field itself in some models. So you have to include, you have to evolve all of them together. Exactly. Yes, that's true. But my point here is that this equation is very simple. The problem is the H and T, they have a non-trivial behavior, which comes from the model. So let's take a look at that. What can we say about this equation without picking any model? I'm just thinking about warm inflation without thinking about any specific model. The interesting thing is that you can actually make some conclusions just by looking at this equation. So this is the number density of dark matter. And again, I'm repeating myself here. T and H are outputs of the warm inflation model. I'm not picking any model here. So this argument is very general. I can go from here to here, rewrite this equation in terms of the heat of dark matter. Now, in other words, I'm dividing this by the entropy of the bath. And remember, we are producing entropy. In warm inflation, you are not in equilibrium. It's a very interesting situation. Anyway, so it's easy to show that the yield follows this equation. And this integrand here is given by this expression. So if you look at this prefactor here, and one more thing, I'm going from a scale factor to number of defaults through this. So my clock is number of defaults because it's an inflationary, so it's easier. So if you look at this prefactor, this is basically the total entropy of the universe, not the density, the total entropy of the universe at each moment. So it tells me that this thing here, it has to be the co-moving dark matter number density. And you can show it, it's easy to show. In other words, what I have here in the integrand is the rate of change of co-moving dark matter number density. So in other words, if the dark matter density is little n, I multiply that by AQ, this is the scale factor Q, remember? So this whole thing is the co-moving number density of the dark matter. And this parameter here, it follows the rate of change of this as a function of defaults. Okay? Now, I'm going to make a claim here, which is very simple. So this function here, this actually tells me how much dark matter I'm producing in a co-moving sense at each moment. If I start deep in the warm inflation phase, like from the beginning of the inflationary phase, as I showed you in one example, and it's a general thing for most of the warm inflation models, C and H, they start kind of at some value and they change very slowly at the beginning. So at the beginning, I can basically ignore the change of these two functions. This is the leading factor when it comes to change of this function. And it's an exponentially increasing function of time. So at the, deep in the inflationary phase, this is a really exponentially increasing function of time. Now imagine you go through all the inflationary phase, everything ends, you're entering the radiation-dominated phase. In the radiation-dominated phase, I know how temperature and Hubble change with the scale factor, right? That's well known. I can plug them back in, and I can show you that this is actually an exponentially decreasing function of time. So this tells me that this function has to peak at some point between these two limits. And that's what's happening. And at that peak, you are producing most of the dark matter. How can I find that point? It's easy. You take this function, you take a derivative with respect to the number of defaults. That's what I did. If you have a function for T and H, you can solve this, you can read off the location of this peak. So this is the first distinction between doing UV freezing from warm inflation compared to the standard UV freezing from radiation domination or in any other non-standard cosmology. Because in all the other cosmology stories, the dark matter abundance comes from the maximum temperature of the bath. It depends on that. In our story, in warm inflation, it doesn't come from the highest temperature. Most of the dark matter is being produced around this peak, which has a kind of has some relationship between temperature and Hubble at the same time. So that was very general. Now I'm going to pick a model and I'm going to show this like a representation of this argument so you can see this in a better way. So I'm going to pick the warm little plasma model. I showed you this plot. Now I have the inputs. I have temperature, I have Hubble as a function of time. I can plug them into this equation. I can plot this function and I can look at the function. So this is basically the rate of the co-moving number density, the change of the co-moving number density. And we try to normalize this function so you see a little hat on top of it so that the maximum number is always 1. So we normalize this function to its maximum. I picked two different little n's. Remember, this n determines the dimension of the non-renormalizable operator. And for each one, I picked the scale lambda so that I can get the right rate abundance today for a dark matter of mass of 100 GeV. This is 60 volts. This is the end of the inflation. This is the beginning of the radiation domination phase, and this is the transition between them. Here, we are deep in the inflationary phase. For n equals to the solid black line, you can see the peak is happening here. Most of the dark matter is being produced after the end of the inflation, before the radiation domination. Okay, that's interesting. You can make a really interesting observation. If I start increasing n, at some point I'm going to enter this region. So the peak of the production happens deep inside the inflationary phase. In other words, you can produce all the dark matter deep inside the inflationary phase from the thermal bath. So let me remind you, We are doing inflation, we are doing exponential expansion, and we have constant entropic production. And the claim is that you can actually produce enough dark matter, all of the dark matter, deep inside the inflationary phase. And this plot shows you the co-moving number density. Remember, this is the rate. In other words, the top is the derivative of the bottom path. And here you get the largest rate at this point, which basically around the peak to produce most of the dark matter, and then it plateaus. Let me show you another plot, which is even better. Now you can look at the yield itself for those two benchmark values. This is the yield of dark matter as a function of equals. Now I'm tracing all the history from the beginning of the inflation towards the beginning of the radiation domination phase. Let's look at n equals 2, black solid 1. This is how it goes. And it plateaus at its final value. This is the freezing that we get. And this is the beginning of the radiation domination. N equals 6 is the dashed one. It goes like this. And we kind of pick the numbers so that they always give me the right amount of dark matter today. We can do a comparison. I can use the reheating temperature with the same number of the same value of these parameters and calculate the amount of yield that I would produce if I start producing at the reheating temperature.
So how did the march at the end? Is that what did you do to keep the march at the end? So did you choose something? Because aren't they supposed to march? I don't think so. At the end, they give you all the same omega hits.
Right. If the mass of the dark matter is fixed, right, the yield has to be the same to get omega. But the parameters are different.
Ah, yeah. So
Right.
like that. So
Right. Yeah.
now
Yes.
so
Yes.
that's you tweak to
Exactly. Sorry for the confusion, but that's fine. So let's do a quick comparison. Let's say I don't care about warm inflation. I want to produce dark matter like the normal way. When I have the radiation domination, I'm going to start producing dark matter. So if I keep all the parameters the same, and I start producing not from here, from the beginning of the radiation domination, let's just compare them. N equals to the solid line. This is from warm inflation. If I start here, I'm going to get this. So there is this amount of enhancement that I would get if I start producing from the beginning of warm inflation. Now let's go to N equals 6. And for N equals 6, this is the one from warm inflation. Now this is the one that I would get just from the beginning of the radiation domination. You can see the enhancement is getting even bigger. And it's easy to show that this is like it has an exponential dependence on the dimension of this operator. And even for dimension 5 operator, when N equals 1, you can see the enhancement is an order of 10. And it's easy to see that you can you can actually show that this ratio that I told you about, let's call it R, it follows, you can get it from this equation. And it doesn't matter what's going on here. The point is that this is a large number, this is a positive number larger than 1. This is a few e-folds, the widths of the peak, and I'm comparing the value of a function at its peak with its value at some other point. So by definition, this has to be larger because it's the peak of the function, it's the maximum. Anyway, the point is that you get this enhancement compared to the radiation domination case. I'm almost done. Here you can see more examples. There's nothing new here. I'm just changing the mass of the dark matter, 2 different panels. There is this parameter Q here, and the Q being the ratio of dissipation rate to Hubble, the upsilon divided by Hubble rate. And you can actually solve the warm inflationary scenario for different dissipation rates, and you can see the effect. I think, again, the point is that if you increase N to sufficient large numbers, you can show that most of the dark matter can be produced before the end of the inflation. Yeah, that was kind of exciting thing that we found. You can get really excited and plot that ratio as a function of the little n. Remember, this n plus 4 is going to be the dimension of the non-renormalizable operator. and you can see that actually the enhancement can become very, very large. Here, I'm comparing the yield of the dark matter coming from warm inflation divided by the yield starting from the radiation dominated phase.
The lambda would become smaller.
Right. And the other thing that you should pay attention when I talk about this like n equals 9, I'm assuming that all the other terms below that they are off somehow. Otherwise, it's an EFT approach. If you have the n equals 1, that's going to be the dominant factor. So to see the effect of individual terms, you have to assume that the lower dimensional operators, they are absent. Okay. I think I'm going to conclude by saying that dark matter production from a thermal bath can be sensitive to the heating phase. A thermal bath can exist during inflation. Primordial relics, including dark matter, can be produced efficiently from the bath through highly suppressed operators. UV freezing from warm inflation provides new ways for reheating to the standard model. And I think the last thing, which was honestly my point of this paper, is that the persistent thermal bath during warm inflation provides an intriguing cosmological setup for phenomenologists. Thank you.
Okay, so questions for Barmak.
Yes.
So when you compared the ratio,
Yeah.
I thought you were in the previous case, you were saying that the T max can be like orders of magnitude greater than the T reheating.
Right.
Should I compare the ratio not with the T reheating but the T max? So in the R function which you just like showed.
What they did in the, let's go back, in the previous papers, they actually look at the same thing, not just the ratio. They look at the ratio of the yield that you get from two scenarios, and they were able to write it down in terms of the ratio of Tmax and T. In our case, you don't see that because the maximum T is actually at the beginning, but you get most of the contribution at some.
No, but I was thinking like the comparison that you do in your denominator, do you compare with the usual RH or should you are comparing with their numerator?
I'm comparing with reheat. I mean, I'm comparing with reheating point. Let's go back to my.
But shouldn't I compare with the numerator? Like if I want to say that I'm doing better than.
I'm not comparing. I'm not saying I'm doing better than them.
You see this,
I'm just comparing my scenario, like what's happening before radiation domination and after radiation domination. I think if you, it's hard to compare this with what they did, but I think if you do, you're gonna get more in our scenario. But I'm not gonna claim that. I think that's.
N equal to 1, you'll get more.
Yes, I think we get more. Yeah. But I think it's right now. I think the setup is not. It's the things that we have. It's you can't easily compare what we did with what they did. Yeah, I'm just doing like the point of what they did was if you start producing something from the bath before getting to the radiation domination point, you're gonna get more. We are doing the same thing here, but we are replacing what they had for the reheating with an inflationary phase.
So it seems that if you are freezing out during the time, so that's basically.
Exactly. It was kind of confusing. We thought about this because if you think about this bath, you produce radiation, it's gonna get diluted, but you keep producing it. So we thought that if you end up with some dark matter, it has to come from the last equal of the inflation because the rest of it is gone. But it is still there. It seems that it's kind of persistent.
But then the question is, maybe one can also address
Baryogenesis. That's a very good point. These people, the people who came up with warm inflation models, they have papers on baryogenesis. Because if you think about it, warm inflation, everything is out of equilibrium. It's a really good setup for baryogenesis. So they have like I know at least there is one paper on baryogenesis from warm inflation.
Because then you can pull in.
Exactly.
Dark matter with the
Exactly. Yeah. Right. Yes.
So how do you define? So you said like every time I'm getting a back reaction from the rho phi. So but I'm still defining some kind of like temperature here. So do you check that the rate of thermalization?
Oh, good. That's a good point. Okay, good. They assume that the thermalization happens fast enough, but let's go back to. This is actually interesting. So there is a condition here. They want the temperature to be above Hubble. So let's say in these models, they check that it's okay, but that's true. You need to check that the thermalization actually is fast enough so that they can define a temperature to describe radiation. That's a good point. But the thing is that one of the things that you want in the warm inflation is this. And if you think about this, it's actually in the right direction of thermalization. If I imagine the rate divided by Hubble, the rate for relativistic particles is actually, it goes with some coupling times T divided by H. So it's in the right direction, but for a different reason. Here, they want to have thermal fluctuations dominating over quantum fluctuations. But it also, it's kind of goes toward that direction. Yeah.
The question. Also, since they build these models like 2021 and all this stuff, so I guess the non-Gaussianity is satisfied in this.
I think that should not be a problem. I think it's still okay. Yeah, yeah. There is one tiny thing which I didn't say because of the time. I didn't want to spend time on that. But in all these models, the radiation that you're producing, it's not the standard model. It's some kind of dark radiation. It's something else. Because of this weird setup that you have to like follow, it's not the standard model. So you still have a problem. You need to go from this radiation to the standard model. So that's one of the advantages of this. You can do some freeze-ins, produce some heavy particles. They're going to dominate the energy density and then you can decay and give you. That said, there was a recent paper on minimal warm inflation. I'm going in the wrong direction. Yes, here. In these models, there is a recent paper. They tried to do this with the QCD SU3. The problem here is that when you want to do minimal warm inflation, if you have light quarks in the spectrum, they're gonna suppress this thermal dissipation rate, which is bad. So you want the quarks to be heavy at the get-go. So which is not the case in QCD. So in this model, what they did, they tried to build a model to start with its QCD SU3. Quarks are heavy at the beginning, and then you make them light later on. So you can do warm inflation with, yeah, but you have to make quarks heavy at the beginning. Yeah, but I think they claim that this is the first warm inflation story with the standard model radiation. Yeah.
So the questions.
Yeah.
So in this model, like, is there a way of connecting the scale of the F where I take this U1 symmetry with the H inflation? Like,
Right.
So do you derive the ratio? Like, do you derive the ratio? Because already I just say that F should be like greater than HI, but I don't really tell like what that.
Right. It comes. It's a yes. It comes from the symmetry breaking. Yeah. Right.
So do I know the scale?
Yeah, exactly. Yeah, there is one thing that you need to be careful because you're picking up a SUN, if you have Yang story, so there is a confinement the scale for that. You need the temperature of this radiation to be above that. You need to do all this before the confinement. So that's one thing that you need to be careful with. Yeah, right.
Okay, so any further question? If not, let's thank the speaker.
Thanks.